Last time we started section 4.3 and we did the greatest common divisor part of the lesson. Today we're going to do the least common multiple part. And to start with, let me just define what the least common multiple is for a set of numbers. The least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. So one way to think about it, and this is going to be one of our methods actually, is if you were to write out the multiplication tables like the kids learn, like 3, 6, 9, 12, if you were to list them all out that way, it'd be the smallest one where they first have that one in common. And that actually is our first method for finding the least common multiple. There are two ways to do this particular method. I'm going to show you both of them. So this is, I totally lied. That was the next method. Actually, I'll go over that one since I've already mentioned it. This one. Let's do intersection of sets first. Okay, so to do intersection of sets method, you list the multiples of each of your values, and then you find the smallest number that they have in common in their lists the first time they meet. Now, as long as they meet pretty quick, this is a very nice method to use. But if their least common multiple doesn't occur until the two numbers are multiplied by one another, this could be a very lengthy method to use. So it works really nice sometimes and not really nice sometimes as well. So we're going to do an example so you can see when it does work nice. We've got the numbers 12 and 15. So we're going to write out, if you will, the multiplication table for 12. Now, that one may be one that you know, right? It starts with 12, and then you would do, that's 12 times 1, and then what's 12 times 2? 24. What would be next? 36, and then 48, 60. Let's go for a couple more. 72, 84, and hopefully you're recognizing, right, that this is an arithmetic sequence. You're adding 12 each time, so it goes back to some of the other things we've talked about in class. We're going to do the same thing for 15. Now, technically, as soon as I find one in my list of 15 that matches one I already did, I could stop. So clearly 15 doesn't match anything. What would come after 15? 30, and then, okay, and nothing's matched yet, right? But what happens the next one? Yeah, and that one matches. So I can stop right there, and this number, 60, would be my least common multiple. Now, notationally, the way this works, I'm going to write down this notation because we're going to be using it a little bit later. But if you write LCM and then you put in parentheses 12, 15, it means the least common multiple of 12 and 15. And that we found out to be the answer, 60. Now, if you just wrote on this LCM equals 60, that's totally fine. I'm just going to be using this notation later, so I want you to get a little bit more comfortable with it in the meantime, okay? All right, let me show you a more visual perspective of a way to do this as well. This is called the color rods method or the number line method. Go back one more. In this method, what you do is you show multiples of all numbers on a number line in intervals of each value. And you find the first value in which the intervals coincide. This is a really good hands-on visual instead of a numerical demonstration. The one I just did, which is pretty straightforward, I think, it still involves us using just numerical, right? I mean, it's just numbers, and we're looking for common numbers to show up. This one would be really good for your tactile learners if you specifically use the color rods for it. Now, there are manipulatives that are actually colored rods. So like, every yellow rod is 2 long, and every orange rod is 3 long, and every red rod is 4 long. Okay, so you could actually like put them end to end, line them up, and you could actually see this method. I'm going to do a visual for that on the screen that's similar, and we'll do it for the numbers we have 6 and 15. So just pick a color. I mean, if you have colors, that's great. If not, don't worry too much about it right now. But we're going to pick a color. And I'm going to make that the multiples of 6. So this is 6 long. And if I put them end to end, right? That's the idea here. And I would put them end to end until they actually matched up to the other number's ending spot. So the way mine did it, and of course this isn't perfect because I'm drawing it on the screen, is that would be 6 long. This all the way to here would have been 12 long, right? And if it went all the way to here, I would be 18 long. And then after 18, where would I be? 24, and my screen's not big enough. I need to add one more rod. So I'm just going to shrink it a little bit to do that. And then our last one, putting 6 on the end here. Again, not visually perfect, but you have the idea, would have been 30 long. Okay, so we're just stacking them end to end. You might be asking me, well, why did you stop at 30? Well, we already did this list, and I know that 30 is in the list of 15s, so I kind of already knew where I was going to head to the answer. If I were physically doing this with a child, I would overestimate. I would put, you know, until we got to like 48 long or something like that. I would make it longer than I needed to. And then the other one that I'm going to do is going to be 15 long, and I'll change my color. The 15 rods, if I had rods for that, would have a different color to them, and I'll put them above. Actually, move this down. So a rod that was 15 long would come to approximately here. And then if I did another one end to end, whoops, it would come all the way to the end here, and I would hit the ending points at the same spot. My diagram's not super convincing, but it would be very convincing if you actually had rods. So you would have all the way to here would be 30. They would hit the same ending at the same time, and then the LCM of 6 and 15 would be 30. Now that's the colored rod version of this method, but you'll notice that the title actually said number line method as well. So I'm going to show you the number line visual for this method. It's very similar, a little bit less of that tactile kind of stuff. It works with the number line. So let me do that one with you. Trying to move it, and I didn't really want it tilted, but oh well. All right, so draw yourself a number line. All right. And of course, it starts at 0. And if you were doing an actual number line where they were all numbered out, that would be great. I don't want to draw hash marks for 30 hash marks particularly, so I'm just going to mark mine on the 6s. Where my jumps, if you will, would be. Okay, so if I were making jumps that were 6 long, we'd have 1, 2, 3, 4, and they would end at every 6, you know, every multiple of 6. And then if I make jumps that are 15 long, I don't have it marked, but I certainly could, right? Here's 15. My jump would land me at 15 and then at 30. And so again, because the jumps ended at the same location, that first location where they both ended would be the least common multiple. Now, if I continue doing these jumps, are they going to end at the same location again? Yeah, at some point they are. And they'll keep happening over and over and over again, right? Actually, every, if you will, 6 or 5 6s. So they'll end here at 30. They would end here again at 60. They'd end here again at 90. It would keep happening over and over and over again. There would be no end to where they would actually end. So we only want the first one, so you want to be careful that you catch the first one and you don't get caught up in making so many jumps that you end up at the second one or the third one along the path. Okay, both of these methods that we've discussed so far are great as long as the multiple shows up pretty quick. Agreed? But I don't want to be drawing or jumping number lines or writing out lists of multiples if the number doesn't actually show up very quickly in that list of multiples. So there are other methods that work in general when our numbers are bigger, maybe a little bit better. So prime factorization we talked about last time. We did it for greatest common divisor. We're going to look at it now for the least common multiple and see how that changes to find that value. So again, you construct the prime factorization. That's what we did before. Now, 2 is different. It says choose all prime factors. Last time we only chose the prime factors they had in common. So that's different. 3 says to list the largest exponent. And the last time for greatest common divisor, we listed the smallest exponent. And then on 4, it's the same thing. We find the product of what we get. Multiply it all out. Okay, so the 2 differences really are right here and right here, the words you wrote in your underlined part. Those 2 things will change what kind of answer we get. And so we're going to do an example. I chose an example that actually I'm using 3 numbers for. You could use 3 numbers for either of these other methods as well. There's nothing special about choosing 2 numbers to compare or 3 numbers to compare. So I chose on this one to compare 3 numbers. The numbers are 90, 50, and 20. So we're going to find our prime factorization for 90, 50, and 20. And I'm going to do the division ladder that I've been doing. Just as a reminder, if you want to do factor trees, more power to you, go for it. Division ladder divides by the smallest prime first, which would be a 2 here. And we got 45. No more 2's, but this one did divide by 3. We did this one actually in class last time. And we got 15. Divides by 3 again, and it gives me 5. So the prime factorization of this is 2 times 3 squared, because there's 2 3's, times 5. Is everybody good with that? Okay. The next number is 50. We're going to do the same thing. It divides by 2, so we'll do that, and it's 25. But then 25 would be 5 and 5. So on this one, we have 2 times 5 squared. And then our last one is 20. And again, it's a 2. And so 20 divides by 2, we get a 10. Another 2 and a 5. So I have 2 squared times 5. Okay, so far so good with everyone. Okay, I'd like you to take a look at all the bases. Okay, so all of the numbers that may or may not have exponents raised to them, but all of the bases here, I'll just underline them all real quick. What we want to do is we want to list all of the prime number bases that we have. So as I'm finding my LCM, the first thing and this is of 3 numbers, right? 90, 50, and 20. What are all of the prime factors that are listed in any of those numbers that are listed below or listed above? 2 and 5 and 3. And I kind of go in order, just that's my OCD part of me. So if you put the 5 before the 3, it doesn't hurt anything. That'll be fine. 2, 3, and 5. And I want to list the biggest exponent that each of them have. So what's the biggest exponent on a 2? A 2, right? I have 2 squared right here. That's the biggest exponent on the 2. What is the biggest exponent on a 3? It's also a 2. It happens to occur in the first number, so that's 3 squared. So I've got a 2 on this one. And what's the biggest exponent on a 5? 2, and it happens to occur in the middle, and that won't always happen. They could occur, most of them, inside of one number, and that would be fine. And the last thing to do then is to multiply that value out. Now, you know what those individual values are. It's 4, 9, and 25, and just because we're still working on those compatible number strategies that you guys had and different mental math kind of exercises, which of these 2 numbers is better to multiply first? I would multiply the 25 and the 4. What's that one going to give me? 100. And then what's 100 times 9? 900. And you don't have to multiply that out by hand. You're welcome to grab a calculator. I just wanted you to see that those strategies that we used can still be used as we continue. Now, I can't verify directly that this is a least common multiple with the work on my screen, but I can verify that it's a common multiple. How can I know for sure that 900 is a multiple of 90? Or why do I know for sure it is? Why is 900 a multiple of 90? Don't everybody talk at once. Perfect. If I multiply 90 by 10, I get 900. Is everybody good with that? Another way of saying it is you could say that 900 divided by 90 is 10. Okay, there's no remainder when I try to do the division. How about 950? Will 50 evenly divide 900? Yes, it will. Will 20 evenly divide 900? Yes, it will. So I can at least verify that this is a common multiple by looking at the numbers and comparing them what I have. So for instance, if at the end here I got 925, you should have like red flags going off. There's no way 925 is the answer. There's an error if I've gotten that somewhere because it's not a multiple, and the one I just came up with is not a multiple of any of them, but it's not a multiple of all of them. Okay, in order to be the least common multiple, it would have to be a multiple of all of them. So this is prime factorization method. Division by primes. I told you last time this is my favorite one for GCDs. It's my favorite one for LCMs as well. Division by primes. I don't know why, but these are not underlined, it looks like. So you're going to write all the numbers in a row. Divide each of the numbers by a common prime factor. Divide all quotients by a common prime factor. Note any factor that divides at least 2 of the numbers can be used to divide the number that's not divisible, simply relisted. We're going to repeat step 3 until no other common factor is found. And again, the LCM is the product of the primes. Okay, so the process for doing this starts out much like the process for doing division by primes with GCDs, just like it did for the prime factorization. I factored them all out. Okay? Does everybody have those written in? Still writing? A couple of you? Okay. So what you do is, whether you have 2 numbers, or in this case I've got 3, we're going to write all the numbers on a row. 90, 100, 20. And we're going to divide each of those numbers by something that divides all of them, smallest prime. So what's the smallest prime that will divide all of those numbers? 2. And we're going to divide them. So this is 45, 50, 10. Now, 2 will no longer divide all of these numbers, right? Neither will 3. 5 will, though, right? So we're going to divide them all by 5. 5 will divide all these numbers. So what's 45 divided by 5? 9. 50 divided by 5? 10. And 10 divided by 5? 2. Now, this is where we would stop if we were finding GCDs. In fact, this is the same problem we did the GCD one on. What would be the GCD of this problem? More. 10. It would be 2 times 5. We multiply both of them together. Does everybody remember that now? That's the GCD process. Now, when I'm doing LCMs, I continue this process. But what I do is I recognize that yes, 9 and 10 and 2 don't all have something in common, but at least 2 of them do have something in common. What do 2 of these have in common still? A 2. Now, the one that doesn't have a 2 in it, we just rewrite it. Okay, we sort of just ignore it. Pull it down, don't mess with it. And the other 2 we divide. So 10 divided by 2 would be 5. And then 2 divided by 2 would be 1. Now 9, 5, 1 don't have anything in common when you compare them 2 at a time, right? Except for 1, which doesn't yield us anything new. So our answer then is the multiplication of all of these numbers, including the ones on the bottom. That's the LCM. So my LCM here of 90, 100, and 20 is 2 times 5 times 2 times 9 times 1. All those numbers multiplied. And what do you get if you multiply all of those? Did I miss one? Oh, I missed the 5 at the end. Thank you. Yes, we should have. Thanks, Abigail. All right, get that last 5 in there. 2 times 5 times 2 times 9 times 5 times 1. What did you get? 900 is right. Just happens to be 900 just like the last one was. And can you check visibly on this one, because it's pretty clean, to check to make sure that at least that it's a multiple. It may not be the least multiple if you've made a mistake, but you can at least see, I keep using the word least and I'm bothered by the fact that I'm using that. At the bare minimum, you can see that 900 is a multiple of 90, 120, right? So you've got at least a viable option here, okay? And it is the correct one. This is the LCM, 900. Now, there is a relationship, as you might have guessed, between the GCD and the LCM. I mean, obviously, I'm using kind of the same methods to do things. I'm factoring things. I'm breaking them down. I'm making lists. I'm using a lot of the same stuff. There's got to be a relationship between what's going on. And there is. There's a formula. The formula that relates the GCD and the LCM together are that if you multiply the GCD times the LCM, it's equal to the product of the two numbers. Now, this does only work for two numbers. So the things that I've been doing on the last couple problems where I had 3 numbers, but we don't have a relationship that this is for 3 numbers. It's only for 2 numbers, so be careful with that. Okay, so we're going to do an example to show you how this formula can be used then to make our process easier. The idea is that if you find one of them, you could use the formula to find the other one instead of recreating the wheel or remultiplying things out or looking for more information because they have this relationship. So in particular, flip back to, we already did this in example 4 last time. So look back at example 4. In example 4 last time, we found the GCD of these numbers, 72 and 126. So this is from example 4. What was the GCD of 72 and 126? 18. Okay, so we're going to use that fact. We're going to use that fact and the GCD-LCM formula to find the LCM. So just shorthand-wise, I'm going to write down the formula. It's the GCD times the LCM equals the product of our two numbers. Well, we know the GCD. That's what I just found, 18. And we know our two numbers. What are our two numbers? 72 and 126. So I should be able to find this one missing piece, the LCM, by using that. So somebody tell me, what is 72 times 126? We'll start there, because those two numbers are just multiplied, simple, in your calculator kind of stuff. 9,072? Awesome. How then would I find the LCM when I get to this point? Yeah, we would divide by 18. So that 9072, divide by 18. What do you get? What is it? 504. And that will be it. Handy, right? So, for instance, over here on, let me take one where we had 2 items. Here, we found that the LCM is 60. Could we find the GCD if I know the LCM is 60? Absolutely, because the GCD times the LCM should equal the product of the numbers. Well, my numbers are 12 and 15, and the LCM is 60. So using that, I should be able to find the GCD. What's 12 times 15? 180. And what would I do then to find the GCD? Yeah, I would divide by 60. So the GCD would be what? 3. That's how you use the formula. Okay? Very good. All right, we have A couple of word problem type examples. I want you to see how to construct greatest common divisor, least common multiple word problems. You should be able to see when you read them what they're asking you for without them saying find the GCD. If it says find the GCD, it means that they have not constructed a problem well. Because the language itself should force you to do that if the problem has been constructed well. And the same for the LCM. So let's read through this one and see if we can decide which one it is, because that's our first question. Which one is it? Am I finding GCDs or LCMs? Two bike riders ride around a circular path. The first rider completes one round in 12 minutes. The second completes one round in 15 minutes. If they both start in the same place, at the same time, going the same direction, and we got to have all that or none of this will work, okay? If they start at different times or they're going opposite ways, none of this is going to work. And if they go at a consistent pace, which means they don't get slower because they get tired, they don't take a break because they need water, okay, they got to keep going at that same pace. After how many minutes will they meet again at the starting place? Okay, so obviously the 12-minute person eventually is going to lap the 15-minute person, right? If anybody's a swimmer or a runner or biker or anything, that's the way that it works, right? You eventually overtake that person. I constantly am overtaken on the track at the GC by the basketball girls or somebody going around much faster than I go. All right, so that will happen. But eventually, if we keep our same pace for long enough, we will meet back at the starting spot at the same time. First question we have to ask ourselves is this a GCD or an LCM problem? LCM, you're right, Cassidy. Why?
Because they meet, like, I don't know how to explain it.
Okay. How about somebody help her?
They spell number line.
You can think about it like a number line.
Yeah.
That's a good way to think about it. You can also think about this as the fact that they're running or doing multiple laps, right? Hence that word multiple. We're continuing this process multiple times. Okay, so good job. So we're going to find the LCM of 12 and 15, and we get to pick a method. Which method do you want to use? What? Number line. These numbers are pretty small, so we are hoping, did we already do 12 and 15 on a number line? No? I did 6 and 15 on a number line, didn't I? Okay. 12 and 15. All right, so if I do 12 and 15 on a number line, let's do 12s first, I guess. I don't know. So if I do 12, and then where would I end up next after 12? 24. It better end in 0 before I stop. Agreed on that? Okay, because otherwise it won't be divisible by 15. It even might not then. What's after 24? 36, and then 48, and then 60. 60 is a viable option for my answer, right? Because it ends in 0. Let's see where we get on the 15s then. So if I go 15, I land somewhere here. Where would I land? I'll put my 15s above. Where would I land after 15? What is it? 30. Whoops. Okay, so I'd be landing at 30. Where would I land after 30? 45. And then after 45, 60. So I do land at the same spot. Therefore, my LCM of 12 and 15 is 60. 60 what? This is a word problem. It's got units. Minutes. So we're talking an hour, right? After an hour of writing, they will both be at the starting point at the same time. All right, let's look at another example. Dr. Haynes makes cupcakes for her students. She makes 20 chocolate cupcakes and 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate, but only one type of cupcake on each plate. What is the greatest number of cupcakes she can put on each plate? So your first question is it a GCD or an LCM? Why? greatest, there's keyword greatest in there. There's another reason you could think to do the GCD here.
It's also like you're trying to divide it up. You're not like getting pixels.
You got it, Emily. We're dividing up the cupcakes, right? So this is a divisor problem. Good, very good. Okay, so we're doing GCD. And we have 24 and 20. How do you want to do this GCD problem? We didn't do any GCDs yet today. Which one? The division. Okay, so division by primes?
Yeah.
Okay, or prime factorization.
No, like the prime factor.
Prime factorization. Okay. Ariel, you're the only one who gave me an answer, so we're going to do what you want to do. That's the way that goes. All right, so prime factorization, what will 20 divide by? Smallest prime. 2, which gives me 10. And then 2, which gives me 5, and then I'm done. So this is 2 times 2 times 5. Or I'll do 2 squared times 5. 24 divides by 2 to give me 12. 12 divides by 2 to give me 6, and then 2 and 3. So I have 2 cubed times 3. Now, when I do GCDs, what I look for is for any prime bases that they have in common. So what prime bases do they have in common? Just the 2. And the smallest exponent on the 2's is a 2, so it's 2 squared. So the GCD is actually 4 here. 4 what? 4 cupcakes. So if you visually think about what this is saying, it will make sense. We have plates of cupcakes, and what we're saying is we're going to put 4 on each plate. Can I put 4 chocolate cupcakes on each plate and have no chocolate cupcakes left over when I'm done? Yeah, how many plates of chocolate cupcakes would I have? I'd have 5. Can I put 4 vanilla cupcakes on each plate and have no left over when I'm done? None left over. Yeah, how many plates of vanilla would I have? 6. So I don't have the same number of plates when I'm done, but the same number of cupcakes are on each plate. Does that make sense? Excellent.